Lesson 9, Applications of Radian Measure. In this section, we're going to be covering 3 different equations that relate to radian measure that are going to be arc length, area of a sector of a circle, and average linear velocity. Each of these equations we are going to relate to other equations you may have seen outside of trigonometry, or that you may be more familiar with. Firstly, with arc length. We have if an arc length of length s subtends an angle with non-negative radian measure theta in a circle of radius r, then we'll have an equation based on s. What we're working with, if you consider a circle, we have a circle with a radius r, and we are trying to find the arc length. The arc length would be the distance around a portion of the circle, a portion that is defined by an angle measure theta. What we should be able to relate this to is another equation that allows us to find a distance around a circle, which is the equation c equals 2 pi r. This is the common equation for the circumference of a circle, which is calculated as 2 pi times r. We've seen 2 pi quite a bit in trigonometry, and 2 pi when talking about a circle refers to what happens when you rotate all the way around a circle. So if your theta value is 2 pi and you multiply that by r, that will give you the full circumference all the way around the circle. Well, if you only want a portion of that, then that portion is defined by the radian measure theta. So instead of multiplying the radius by 2 pi, if you only go around by theta and multiply that by r, then what you're going to find is not the full circumference. You are going to find the arc length of a particular portion of it. That will be our equation for s. S is equal to theta times r, or r times theta. For the area of a sector of a circle, similar concepts. We're still working with a circle with a radius r, and we're trying to find for any sector that is subtended by an angle with radian measure theta, we're trying to find the area of it. So still working with this picture here. However, if we're trying to talk about area, there is another formula for area concerning a circle that may be more familiar. That is A equals pi r squared. This is the actual formula for the full area of the circle. Well, we're going to do something similar that I just did with circumference, where I had replaced 2 pi with whatever radian measure we are working with to find just a portion of it. In this case, I'm going to try to find a way to replace 2 pi again with whatever radian measure I have to find this area of a sector. However, in this formula, I don't have 2 pi. But I can if I do a quick adjustment. If I take this formula and I multiply it by a fraction of 2 over 2, I will get 2 pi r squared divided by 2. Again, this would relate to a full rotation of a circle, 2 pi. That can give me the area for the full rotation. But if I only want to go a portion of the way around, then I would want the area for a sector to be just theta, defining my portion, times r squared over 2. And that will be my area of a sector. Lastly, we have average linear velocity. We have for an object moving on a circular path of radius r with constant average angular velocity of theta divided by t. The average linear velocity is going to be given by the following equation. So what we do have for velocity is more commonly referred to as the distance over time. That's typically what the formula for velocity refers to. Think about miles per hour, something like that. That would be a distance out of time. We are also going to be considering this as a distance over time. The distance that we are traveling, however, is the distance around the circle. Well, the distance around the circle we have already just defined as arc length. So we can think about distance in this case as arc length. And for time, we'll just keep that as the same fraction. We'll just keep time as just a variable t. So for average linear velocity, you can think about that as s divided by t for the arc length divided by t. Or you can also think about that as theta times r over t, replacing arc length of s with what it equals as theta times r. Or you could even sometimes consider this as r times theta over t, as this is another way to write r times omega bar, which is called the average angular velocity. All of these are formulas for the average linear velocity. The most common one, though, is this one here, r times theta over t. The reason why we call this the average angular velocity, because when you're working and rotating around some object, the speed typically tends to change. Maybe you're accelerating or decelerating at any given time. Average angular velocity is just the average velocity you have over that entire period of time, not considering acceleration and deceleration. An important note about each of those equations for arc length, area of a sector of a circle, and average linear velocity. In each of the definitions, we refer to a radian measure of theta. That is because those equations are only defined for radian measure theta. If you instead are working with degree measure, there are versions of these equations that are adjusted for degree measures of alpha. Keep in mind that if you want to change from degree measure to radian measure, so if alpha is in degrees, if you want to change that into radian measure theta, then what you would do is take that degree measure and multiply it by pi over 180. So that would be alpha times pi over 180. If you go back to each of those previous equations and replace every instance of theta with alpha pi over 180, that is where you get these three variations of the arc length, area of a sector of a circle, and average linear velocity formulas. However, it is not recommended to memorize these formulas in degree mode. Instead, it is recommended to understand how to change a degree measure into radian measure first, and then when you have it in radian measure, use the aforementioned formulas.